Welcome back, students. I am Dr. Muhammad Uzair, and today I am going to continue from the previous class. In the last class, I was discussing about the energy analysis of a closed system. So, when we have a closed system, there is no energy interaction due to mass. The only energy that is crossing the boundary is due to either heat or work. So, if I am going to write the energy balance for a closed system, then it will be like this one. We have energy in minus energy out, means the total net energy transfer by heat, work and mass. But when we have a closed system, then there will be no mass. Remember, there will be no mass. So the change in this energy transfer will be equal to the change in the energy of the system. And when we are talking about the change in the energy of the system, so it's mean we are talking about the internal energy, kinetic energy and the potential energy of the system. So for a closed system, it will be like this one. The energy in or the energy out will be equal to the energy transfer due to heat, means there is either Q in or Q out, or due to work. There is no energy transfer due to mass in a closed system. Or in the rate form, I can put a dot on the top of the energies. But here, if you can see here, this is the energy transfer by heat or work. I can put a dot on it. You can see a dot here, even a dot here. So this is basically energy transfer or the rate of net energy transfer. But when we have a delta E system, so I'm not going to put a dot on it. Whenever we have a dot, so it's mean there is a flow. There is a flow. But when we are talking about the system energy, so there is no flow of the energy. Rather, there will be a change in the energies with respect to time. That's why I'm going to put a d by dt. So you can see here, it's d by dt for the energy of the system. The energy of the system doesn't flow. So we cannot put a dot on the top of energy system. So there is no dot here. Other than we have to put d upon dt. But as we know that these energies that are crossing the boundary, they are basically flowing. So I can easily put a dot on it. For a closed system undergoing a cycle, if there is a cycle, then the initial and the final states are same. So it's mean that the delta E system will be 0. If the initial and final states are identical, then there is no change in the energies of the system. Inside a system, there is no change. Now, if there is no change, then the energy balance will be equal to energy in minus energy out equal to 0, because there is no change in the energy of the system. Or I can say that the energy in must be equal to energy out. So the amount of energy that is coming in must be equal to the energy that is going out. So this is for a cycle. Noting that a closed system doesn't involve any mass flow across its boundary, the energy balance for a cycle can be expressed in terms of heat and work interaction. So you can see there is no mass at all for closed system. But when we will study the chapter number 5 deals with the energy balance for open system. Then we will study the mass flow rate as well. Now we have a simple question here. We have a piston cylinder device that contains 25 grams of saturated water vapors. 25 grams of mass is given of the saturated water vapor. Water vapor, so it's mean we have to check the properties from table, rather than we can't use the ideal gas equation. Now we have a 25 gram of saturated water vapor that is maintained at a constant pressure of 300 kilopascal. So in this case, the pressure is constant, which is 300 kilopascal. A resistance heater within the cylinder is turned on and passes a current of 0.2 ampere for 5 minutes from a 120 volt source or supply. So we have an electric work as well. At the same time, a heat loss of 3.7 kilojoule occurs. So there is Q out as well. Now, in the part 1, we have to show that for a closed system, the boundary work and the change in the entire energy, which is U, and the first law relation can be combined into one term, which is called H or enthalpy, for a constant pressure process. And then in second part, we have to determine the final temperature of the steam. Now, in the part 1, we have to use the first law relationship. First law relationship is simply Q minus W equal to delta U. In the first law relationship, we have to put the plus or minus sign depending upon either Q is going in or Q is going out, or the work done is by the system or work done on the system. So we have to use the formal convention of the heat transfer. Normally, whenever we have a piston cylinder device, so typically the piston cylinder device involves a moving boundary, and thus boundary work as well. Because when we have a piston cylinder device and there is a heat transfer, then either the piston will go up or will go down, and you will get a boundary work. So for this question, if I'm going to draw the schematic, so it will be like this one. I have a piston. This is a piston and this is cylinder. So I have a piston cylinder device. Water is filled. The mass is 25 gram, while the pressure P1 and P2 are 300 kilopascal, and we have saturated vapors. We have an electric work, and in this wire or in this electric heater, the current is flowing, which is 0.2 ampere with a source of 120 volt, and the total time to turn on this electric heater is for 5 minutes. So for 5 minutes, this electric heater is turned on. So there is an electric work as well. If I'm going to draw a PV diagram on it, so it will be like this. I have a state number 1, which is like this one. So it's we have a constant pressure, so it's moving like this. You can see from here to here at 300 kilopascal. Now, in the part 1, here, if you see, it is requested to find out a relationship that we can combine the work and U, and we can make it as enthalpy. So if I'm going to write the first law relationship, so either the energy balance or the first law, this is the energy balance, but I'm not using it, I'm just going to use this one. This is for first law. So simply we have Q minus W equal to delta U, and there is no kinetic and there is no potential energy for the system because we are treating it as a stationary system. So we have Q minus W. But in our case, we have two different work. We have electric work and we have moving boundary work as well. So here you can see I have two work. So and this is Q, the heat transfer, the heat flow, minus W other, which is like a W electrical, minus WB, which is the boundary work, and on the other side it's simply U2 minus U1. It's simply U2 minus U1. That is the change in the entire energy. For a constant pressure process, if you remember, the boundary work is simply P V2 minus V1 or P delta V. So this is the boundary work. I am simply going to put the value of WB here. So after substituting, I get like this one. So here I have Q minus W other or the W electrical minus P naught V2 minus V1, where P naught is the constant pressure. And then we have U2 minus U1 on the other side. Now if I am going to shift the boundary work value from left hand side to right hand side, so I can shift like this one. So by simply shifting the values of P V2 minus P1 on the other side and by combining, I can simply rewrite U2 plus P2 V2 minus U1 plus P1 V1. So we have Q minus W, and on the other side we have this type of relationship. Normally this U plus PV is equal to H, where H is the enthalpy. Enthalpy is always equal to U plus PV. So if I'm going to replace this one, I will get H2 minus H1 or Q minus W equal to delta H. So this is the relationship where I can simply show that the boundary work and the entire energy can be combined and we can write the equation in terms of enthalpies. And this equation, because I was using the first law relationship, so I didn't put a negative sign for Q because the heat is going out. I didn't put a negative sign. But when you are going to solve the numerical, then you have to put a negative sign. But if I'm going to use the energy equation, then you have to put a negative sign with this Q. Now in the part B, we have to find the final temperature. The initial pressure is given, the initial volume, initial mass is given, the final mass is given, final pressure is given, as well as one more condition is given, but initially it is a saturated vapor. So for part B, this is the energy equation. I am basically writing the general energy equation, and then I can easily neglect the mass term. So with the energy equation, we have electric work which is coming in, we have boundary work, and then we have the amount of heat that is going out. On the other side, we have delta E system, which will be equal to delta U only. So simply it will be like this one. We have Wn, which is electric work only. Then we have energy out, that includes Q and W, the W boundary work. So we have W electrical, which is N, minus Q out, minus WB equal to delta U. And we have to find the temperature, the final temperature. So for a constant pressure process, I can shift and make or combine the boundary work and the internal energy terms, and I can write in the enthalpy form as we already proved in part A. So it's simply W electric, which is coming into the system, minus Q out, which is going out, and then we have delta H, the change in the enthalpy, or I can write in terms of specific enthalpies as well. So we have H2 minus H1 times the mass. Mass is given, and then we have to find the enthalpy values. Now here we have Q out, which is already given, but we don't know about W in, and we don't know about H2 and H1. W in, which is the electric work. If you remember the basic electric course, then we have a formula for the power, and the power or the electric power is simply VI, the voltage times current. While the power is the rate of change of work, the power is W upon T. So if I have to find the work, so simply I have to multiply power with time, while power is VI. So the boundary work is simply, the electric work is simply VI times delta T, which is the time, and this one is the voltage times current. So we have power and we have time, and when you will multiply power with time, you will get electric work. So here voltage is given, which is 120, I is given, which is 0.2, and delta T is given, which is 5 minutes. But in SI system, we normally use the time in term of second. So 5 minutes means 300 seconds. 5 multiplied by 60, so you will get 300. So if I'm going to multiply 120 by 0.2 times 300, then I'll get a value. But you have to divide it by 1000 to get in term of kilo. And just dividing it by 1000, then you will get a value in term of kilo. So it's 7.2 kilojoule of the electric work, which is going inside the system. Then we have minus Q out. The Q out value is already given in the question. Now M is given, but we don't know about H2 and H1. So how we can find the value of H1 and H2? The H1 is basically at the state number 1. At the state number 1, the pressure is given, as well as the condition is given that the state 1 is saturated vapor. So the pressure value which is given is 300 kilopascal. So you can see here, this is 300 kilopascal. So we have to check this saturated vapor, which is somewhere here, and then we have to check the value of H1 somewhere here, and you will get this one, which is 2724.9 kilojoule per kg. This is in term of kilojoule per kg. You can see here on the top we have a value of kilojoule per kg. So 300 kilopascal with the saturated vapors, you will get a value of 2724.9 kilojoule per kg. So this is your H1. So P1 is 300 kilopascal with the saturated vapor. So H1 is simply Hg at 300 kilopascal, and you will get this value. Again, I'm using a table A5. This is A5 for saturated water pressure table. So we know what is electric work. We know what is the Q out. I know what is the mass value. Even I know what is H1. So if I'm going to put the values in this equation, then by rearranging, I can find out the value of H2. So by solving the equation, you will get the H2, which is 2864.9 kilojoule per kg. So the final enthalpy is given. So now we have final enthalpy and we have a final pressure. The final pressure is 300 kilopascal because the pressure is constant. Now the problem is how we can find the temperature if pressure and enthalpy values are given. Now again, as we know, the H2 is more than H1 at the same pressure. So it's mean the state number 2 is in superheated state. The H2 is more than H1. So we have a superheated state at point number 2. So we are going to use table A6 to find out the value of temperature. Here we have different blocks. So if you can see here, we have a pressure of 300 kilopascal or equal to 0.3 megapascal. So you have to use this block. So we have this block. Now, last time we were using the temperature value and we were checking the the volume or the enthalpy. But in this case, enthalpy is given. As we know, the H2 is given, and we have to find the temperature. So value of H2 which is given is basically equal to 2864.9, 2864.9. So here, if you see, we have 2864. We don't have any value, but we have 2865 here. So 2865.9, and our value was 2864.9. So it's almost close to this one. Almost close to this one. So we have like this one. So at this pressure, which is 300 kilopascal, and with this H value, the required temperature is this one. So the final temperature is 200 degrees Celsius. If anyone is interested to get the accurate value against 2864.9, then we have to interpolate between these values, and with the help of interpolation you will get the exact value. But right now it is very close, so we can assume that the final temperature is 200 degrees Celsius. So this is our answer. Moving to next question. In this question, we have an insulated piston cylinder device. We have insulated, so it's mean there is no Q in or there is no Q out. Whenever the device is insulated, so there is no heat transfer. Now the piston cylinder device contains 5 liters of saturated liquid water. We have saturated liquid water and initial volume is given, which is 5 liter or 5 divided by 1000 meter cube. The pressure is given, which is 175 kilopascal, and it is written as it at a constant pressure of 175 kilopascal. So during the process the pressure is constant. Now water is stirred by a paddle wheel. So we have a paddle wheel, so there will be a work by paddle wheel. While a current of 8 ampere flows for 45 minutes through a resistor placed in the water, there is electric work as well because the current is flowing. Now, if one half of the liquid is evaporated during this constant pressure process, and the paddle wheel work amounts to 400 kilojoule, determine the voltage of this source. There is no Q. The pedal work is equal to 400 kilojoule. Current is given, the value of current is given, and you have to find the value of voltage while the pressure is constant, which is 175 kilopascal. And the question, it is also requested to find out or show the process on the PV diagram with respect to saturation lines. So if I'm going to write the energy equation or the energy balance, so it will be like this one, or it will be like this one. We have the electric work which is coming in plus pedal wheel work which is coming in, then we have boundary work. Remember, whenever we have a piston cylinder device, then the boundary work will be there. Typically all the piston cylinder device involves boundary work. And then on the right hand side we have only delta U, because there is no kinetic and there is no potential energy of this system. Pedal wheel work is given, and the electric work voltage value is not given. While in the question it is mentioned that the process is constant pressure process. So if it is constant pressure process, then I can simply combine these terms, as we have already solved in the previous questions. So I can rewrite the equation like this. So we have the electric work which is coming in plus pedal wheel which is coming in to the system, and then it must be equal to m times the change in the enthalpy, change in the specific enthalpy. So if I can get the values of H1 and H2, then I can easily get the electric work, and then we can find the value of voltage. Now, in order to get the enthalpy values, we have to use the data that is given. In the question, the pressure is given, and it is also mentioned that at state number 1, we have saturated liquid. Remember, in the question, the value of mass is not given, but the initial volume was given. Now, with the given pressure, or with the initial state, I have to use the table A5, this one. Why I'm going to use the table A5? Because it is about the saturated liquid pressure table, and pressure is given. On the PV diagram, it will be like this one. We have a state number 1, then we have a straight horizontal line for the constant pressure, and then we will reach at a point which is point number 2. At this point, 1/2 of the liquid is evaporated. So we can say that we have a X value of 0.5, or the quality of the steam is 50%. Now, at state number 1, at this point, now we can find the value of H. It's simple. As we know, the pressure is 175 kilopascal. You can see on the screen we have a pressure of 175 kilopascal. So here I'm going to check two different values. One is the value of the enthalpy or the specific enthalpy at point 1, as well as I'll check the specific volume as well, because initial volume is given, and when I'm going to divide the initial volume by the specific volume, I can get the mass of the water in the device. We have the saturated liquid at point 1, so we are going to check the saturated liquid value. So here you can see I'm just checking the value of HF, and against 175 kilopascal, the value of HF is 487.01 kilojoule per kg. Now if I have to check the specific volume, so it will be like this. We have 175 kilopascal, and the value of Vf, or the saturated liquid value, is simply this one, which is 0.001057. So I can write like this. At 175 kilopascal with saturated liquid, the value of H1 and V1 are already mentioned here. Now we have the value of H1 and V1. So I'm going to find out the value of mass. Before going to find the value of mass, I'm also going to check the value of H2 here. For H2, the state number 2 is basically inside the dome. So it means it is still saturated liquid. But whenever the value of X is given, then we have to use the formula to get the value of enthalpy. Inside the dome, if the value of X is given, then H will be equal to HF plus X HFG. So at 175, I can check what is HF as well as I can check what is HFG from here. So these two values are mentioned on the top table. We have HF which is equal to 487.01 and HFG which is equal to 2213.1. So with the help of formula, the formula is given here, which is HF plus X HFG. So simply we have to put the values and we will get the value of H2. So we have the value of H2 here. H1 is already determined, so we have the H2 now here. But still the mass value was not determined in the previous slides. So mass is simply V1 upon V1, the initial volume divided by the specific volume at state 1. So simply it's 0.05 meter cube divided by 0.001057 meter cube per kg, and at the end you will get 4.731 kilogram of the mass inside the piston cylinder device. Now we have all the values. After this one, we have to simply put the values in the equation and then we can solve to find out the value of voltage. So you can see here we have the electric work, which is VI delta T. Then we have plus of pedal work, which is 400 kilojoule. We have on the other side we have mass times H2 minus H1. Simply dividing this one or solving this one, you will get VI delta T, which is equal to 4835 kilojoule. So this is kilo, 4835 kilojoule. So when you are going to find the voltage, simply you have to divide this one by this one. Sorry, you have to divide this one by this one. So 4835 divided by I times delta T. So we have 8 amperes times 45 minutes times 60 seconds. But here I am going to multiply with 1000 because we have this one in term of kilo. So we have kilo, so you have to multiply with 1000. Ultimately you will get the final value of the voltage, which is equal to 223.9 volt. So the final or the supply voltage is 224 volt. The energy balance or the energy analysis is basically depends that how you can apply the equation. The energy balance is simple. We have the energy in minus energy out equal to delta E system. You have to check the energy values that is coming in, then you have to check the energies that is going out from the system, and within the system we have only entire energy change, because in most of the cases the systems are stationary, so there is no delta kinetic energy and the delta potential energy. Now next question. Sorry, no, okay, this one. In this question we have a piston cylinder device initially contains zero point 0.8 meter cube of saturated water vapors at 250 kilopascal. Now in this case we have piston cylinder device, initial volume is given, and we have saturated water vapors at 250 kilopascal. At this state, the piston is resting on a set of stops, and the mass of the piston is such that the pressure of 300 kilopascal is required to move it. Now heat is added to the system until the volume doubles. So here if you see, we have a piston cylinder device. Initially the pressure is 250 kilopascal and the piston needs 300 kilopascal, otherwise it will not move. So it's mean in the start, the heat that is going inside the system will increase the pressure of the system while the system is at constant volume, because piston is not moving at all. The piston is resting on the set of stops and it is not moving upside because the pressure is less than 300 kilopascal. When the pressure reaches 300 kilopascal from 250 kilopascal, then it will start moving upside. Then there will be boundary work, and then we have a constant pressure process. Normally for piston cylinder device, we say that we have a constant pressure process. Now here you have to show the process on a PV diagram with respect to saturation lines and determine the final temperature, the work done during this process, and the total heat transfer. Now here if you see here, it's about saturated water vapor at 250 kilopascal in the initial state. So if I'm going to write, or if I'm going to draw a PV diagram, sorry, this is all about the energy balance first. So energy balance is simply we have in minus out equal to delta E system, and here we have in, which is Q in, the heat is going inside, minus the boundary work which is going out. Then we have delta U. There is no electric or there is no other work involved in this question. We have like this one, or I can simply say that this delta U is M U3 minus U1. In the question, basically we have two different sets. We have state 1, which is 250 kilopascal and saturated vapor. Then we have state number 2, which is 300 kilopascal with the same volume, and then we have third one where volume is doubled. So we have V3, which is equal to 2V1 or 2V2, because V1 and V2 are same. And during the second phase, the pressure is constant at 300 kilopascal. Now if we have Q in minus W out, and then we have M U3 minus U1, so I can write the equation like this one, because I have to find the amount of heat that is going in, but we don't know about what is U1 and U3, as well as we don't know about the boundary work. We have to find the final temperature, and for the final temperature we have to use the steam table. Even for U1 and U2 we have to use the steam tables. So moving forward, this is the PV diagram. Here if you can see, we have a state 1, which is 250 kilopascal saturated vapor. Now heat is transferred and it is moving up at a constant volume until the pressure is 300 kilopascal. Until the pressure is 300 kilopascal. After 300 kilopascal, the piston will move upside, and then it will move like this one. And during the process 2 to 3, we have a constant pressure process. The piston cylinder device normally follows a constant pressure process. So we have like this one, and at point number 3, we have a volume which is twice the volume at point number 2. So volume here is doubled as we have the volume at point 2. So this is the PV diagram for this case. Here, if I have to check the properties of the water at point 1, so we have to use the table A5 again, because this is all about saturated water and pressure table. So at point 1 we have 250 kilopascal. So where is 250? 250 is somewhere here. This is 250, and we have saturated vapors. We have saturated vapor, so this is saturated vapor, and we can get the value of Vg like this one. So this is the volume at point number 1. The volume at point number 2 is the same as we have at state 1, because we have a constant volume process. So V1 is like this one. If I'm going to check the enthalpy or the internal energy, so I can easily check. So it will be like this. The internal energy is simply Ug, because we're talking about the vapors. So we have Ug, and you will get this one, which is 2536.8 kilojoule per kilogram. So this is state number 1. At state number 1, we know what is V1 and U1. Now after state 1, we know at state number 2, the volume is V2, which is equal to V1, which is equal to 0.71873 meter cube per kg, and the pressure is 300 Kelvin. So we have a table of 300 Kelvin. But the problem is, at state number 2 and even at state number 3, we have superheated. So either we have to use this one or not. First, I'm going to check the mass at point number 1. So mass is simply the volume upon the volume. We have the capital volume, which is given as 0.8 divided by the 0.71873, the specific volume, and you will get the mass of 1.113 kilogram at state number 1. Now if V1 is 0.8, then the final volume will be the double of 0.8, which that's why the V3 will be equal to 1.6 meter cube, because it is doubled. The double of V1, so I'll get 1.6. So you can see here it's 1.6, and we have a closed system, so mass M1 will be same as M2, and it will be same as M3, because there is no mass transfer. So we have V3 divided by M3, which is equal to M1 as well. So we are getting V3 upon M3, and we will get this specific volume, which is equal to 1.4375. So you can see this volume is more than this one. The V3 is more than Vg. That's why the state number 2 is in superheated state. So state 3 is in superheated region. So for superheated region, we have to use table A6. So if I'm going to check the table A6, so this is table A6. Right now the pressure is 300 kilopascal. So this is the 300 kilopascal or 0.3 megapascal. So I have to use this one. But the problem is, we don't have any temperature value. Rather, we have the V3. Now with the help of V3, which is somewhere here, the exact value of V3 is not given. So it's in between these two values. We have V3, which is in between these two values. So our final temperature will be in between these two values. So as the V3 is in between these two, so our final answer will be in between these two given values, between 600 and 700. As you can see here, the pressure, the volume at point 3 is 1.4375. 1.4375. So this is 1.49 and this is 1.34. So the obtained value is not close to anyone, so we have to find the accurate value with the help of interpolation. So if I'm going to apply the linear interpolation, I'll get a temperature of 662 Celsius. If I'm getting the T3, which is 662 Celsius, so in the same way I have to interpolate for U value as well, which is somewhere here. You can see the mouse. So with the help of these two values, you have to interpolate again to find out the value of U3. So you have to apply this linear interpolation to get it. So T3 is there. So this is the required value. So one part is already solved. The PV diagram is already shown there. So this is the final temperature. Now in part B, you have to find the work done. But for process 1 to 2, the work done is 0 because it is a constant volume process. And for constant volume process, we don't have any work. For the process 2 to 3, we have a constant pressure. And for constant pressure, we can simply find out the work by using formula, which is equal to work is equal to P times delta V, like this one. So we have P V3 minus V2. There is no work involved during process 1 to 2. So between 2 to 3 we have P V3 minus V2. We know what is V3, we know what is V2, even we know what is P2 or P3. Both are same, constant pressure process. So I can simply find out the values like this one. So this is the 300 kilopascal and this is V3 and minus V2, and then you will get 240 kilojoule. So this is the boundary work. In part C, we have to find the total heat transfer. For the total heat transfer, we can use the energy equation that we have already used on the first slide of this question. So energy equation is like this one. So rearranging the energy equation, we have Qn, which is equal to M U3 minus U1 plus boundary work. Boundary work is already this one. We have the boundary work, which is 240 kilojoule. We have already find out the value of mass, which is 1.113. U3 is there and U1 is there. We have already solved for U1 and U3. So just by putting the values, you will get the value of Qn. So Qn, or the heat transfer going inside the system, is simply 1213 kilojoule. So in this way we can solve the closed systems. If we have the closed system and you have to find either Q or W, so it always start from the energy equation, which is En minus E out equal to delta E system. Then check what you can neglect. If there is any value that you can neglect, simply neglect it. Write the equation, arrange the equation, and check what you can find from different sources, either from stream tables or from ideal gas equation. And then in this way you can easily solve these type of questions. Inshallah, we will start the new topic in the next class. It will be about specific heats. So for any queries, please contact, and please don't hesitate to ask anything. Thank you very much.